Recording now. Right. So far we have understood the fundamentals and tried to connect the dots. Right. Today we are going to learn assumptions of linear regression algorithm. So every algorithm will have its own capabilities. It will assume something beforehand. Right. If the data is satisfying those assumptions, then you can use that algorithm. Rather, that algorithm is not going to fit. Okay, so we are going to take the linear regression algorithm and understand, how you need to actually. This is one of the ways to think on whether choose an algorithm or whether an algorithm actually fits or not, or how to choose an algorithm is kind of, we are trying to understand a specific example of linear regression. Okay, so assumptions of linear regression. What are the assumptions of linear regression? There are 5. Okay, linearity. It assumes that there is linear relationship between all input variables and the output variable. Right? If you take this particular example, right, there are we need to predict salary. Let me try to find this. I think that I changed the data a little bit. So there is employee.
Can you share the screen, sir?
Okay. Okay, I forgot. So, sorry. Maybe I'll stop recording and then I will start. Oh, no need. We'll start again. Okay. Now you can see, right?
Yes, sir.
Thank you.
I forgot. So, assumptions of linear regression, right? Assumptions of linear regression, why we are trying to understand, because every algorithm will have its own capabilities or strengths and weaknesses. So how the strengths and weaknesses will come because of the assumptions it has got. Okay, so we have taken the linear regression as a specific example and trying to understand the data and then the algorithm's capabilities, and shall we use this particular algorithm for this data or not. Similarly, for every algorithm it will be there, but we are specifically understanding for linear regression assumptions because linear regression algorithm is majorly used to get inference about data rather than trying to predict and build big models. Okay. What is inference? Whether data is linearly related or not, or which algorithm should I use. That understanding we can get when we actually build linear regression algorithm. How? We'll see today. Okay. So every algorithm will have its own assumptions. Based on the assumptions, it will have strengths and weaknesses. Whether the algorithm can be used for particular data or not can be decided based on the algorithm's capabilities and weaknesses. Okay, we are taking linear regression and trying to understand that concept because linear regression algorithm is used majorly for inferential purposes rather than building a model and trying to trying to use it as a model in real time, because most of the times data is not going to be linearly related to target variable. Okay, so there are 5 assumptions of linear regression. One is linearity. It assumes that all the input variables, in this case we have designation, experience, aggressive behavior score, activity score, and lines of code. All these features are linearly related to salary. When I say all these features are linearly related to salary, can we find whether they are all linearly related to salary or not? Do we have any tools to find it out? Do we have any tools to find whether all these input variables are linearly related to salary or not?
Plotting, scatter plot.
Yeah, scatter plot, and if the input variable is numerical, because salary is numerical, quantitative, correlation test and scatter plot. If the input variable is categorical and target variable is numerical, ANOVA test, right? In a classification problem, chi-square test or ANOVA test, right? all these will give you. But the problem here is linear regression algorithm assumes that all the input variables together are linearly related to target variable. All together. Designation, experience, average behavior, activity score, and lines of code all combined together linearly related to target variable or not. That's what it assumes, that it is linearly related, and then it tries to fit a straight line through data. So do we have a tool to understand that? So far, whatever we understood in the concepts we understood, do we have a tool to understand all together linearly related to target variable or not?
No, I think we have.
No, right? Today we'll see that. Today we'll see that. This is called as multivariate analysis or regression analysis. Okay? So now these correlation tests, they are also analysis, regression analysis only, but this is the real multivariate regression analysis. Okay? So this linearity is one assumption. Based out of this assumption only, we are going to understand whether they are linearly related or not. Okay? This is first assumption. When data is linearly related, when I say the first assumption is linearity, when data is linearly related, algorithm will give you maximum predictive power, maximum predictive power. We got 94, right? Because data is linearly related. If data is even more linearly related, all those input variables now with the target variable, then we would have got 99% accuracy. Okay? So this is one thing. And the second assumption is homoscedasticity is there in the data. Homoscedasticity is there. Heteroscedasticity should not be there. Homoscedasticity is there. I'll explain what is homoscedasticity, heteroscedasticity. I'm missing a image here. I'll put it back. No? Normal distribution of error terms. Right? When you built an algorithm and calculated error, the error should be normally distributed. Okay, that is third assumption. The fourth assumption is, serial correlation or auto correlation should not be there. Serial correlation or auto correlation will be there in the data sets where time series algorithms will work. Okay, we'll cover time series in RNN. I am not going to cover the time series, those Arima and all those models, because they are not that powerful. Okay, when you want to use it in real time, we should be using RNN. It is going to be at the end of the course. Okay, so when the serial correlation or auto correlation is present in the data, linear regression algorithm will not work. You should not be using linear regression algorithm to build a production, model. Even if it works on the train set and test set for now, it may fail at some point in time because of auto correlation or serial correlation. And multicollinearity, multicollinearity should not be there. But multicollinearity is not a problem. Multicollinearity means if more than two variables are correlated with each other, then you call it as multicollinearity. Okay? We'll see all these concepts. Right? These are all again, kind of statistical as well as machine learning. Right? There is overlap. Right? This is overlapping area. So we learned statistics. We learned what is machine learning model and how to build it. Now we are looking at overlapping area, and we'll actually move on to machine learning. Okay, so we are slowly, getting there, right? So we need to understand these concepts to make our existing whatever the theoretical concept more solidified. Okay, and this was a very important question in 2017 and 18. Right? What are linear assumptions of linear regression? That's a very important, regularly asked question. Nowadays they are not asking it, but still theoretically we need to understand. There are many things we need to understand. I'll explain. Give me 1 second. I'm missing an image there. I'm going to replace that, and then I'll come back to this. I think I should put this whole thing there. I already kept it. Okay, maybe not there. So, give me 1 second. Okay, so I'm still using the OLS algorithm. Okay, just to see, it is just for building a linear regression algorithm. Okay, no, there is nothing big there. So I'm still using OLS algorithm. You know how to use OLS algorithm. See this? This is the target variable, and these are all input variables. I'm not using the employee number. Is that a right decision as input variable?
Yes.
Yeah, we don't need to use.
Yeah. So then, right, I built a model. When I said fit, it is going to form those equations and solve all of them and find out whatever. In summary, we see the R square score. Right? We have previously, when we used only experience and only other behavior or some feature, we had got 90% accuracy. Now it got 94% accuracy. At R square score 94%, but adjusted R square is 92 only. That means most of it, right, the 2%, right, whatever the extra 2% is because of adding more features. That's the drawback with R square score. Do you remember? R square score tends to increase when you add more features, even though features are important or not. So adjusted R square will nullify that additional effect of adding more features. When you look at the formulas, right, you will understand what I'm actually talking about. Any questions there on R square and adjusted R square? Should I repeat it, or are you guys clear? Because R square, adjusted R square, question will be asked in interviews. Now, for regression problems, R square, adjusted R square, RMSE are the best measures to see whether model is working good or not. Any questions? Move on. Okay. So now F1 score and all, we don't care now. See this now here. Intercept, there is some number, right? Minus 8.4 E plus 0.4 means what? Minus 8.4 into 10 to the power of 4. Okay, it is 8,000, 84,000, I think, right? 10 to the power 10 to the power 4. 10 to the power 4 means 4 zeros. Right? Here 3 zeros will come. 84,000 minus 84,000 is the intercept. Okay. P value, see this? Is this needed? Intercept needed?
No.
No, right? Because
No.
more than
Logarithm.
0. Yeah. So designation. See this designation. What happened to designation? Why we have got that many column names for designation?
Each column probably is taken as one of the input parameters.
By
Sorry.
bit
Maybe one hot method or something like that.
One hot encoding, right? That's a good. That's yeah. I am just checking whether you remember or not. Or are you focusing or not? I'm just checking. Okay, so it is one hot encoding, right? By default, OLS algorithm takes the categorical columns and does one hot encoding. Even when there is ordinality in the data, what is ordinality? Hierarchy is there, right? The designations are basically hierarchy. It is strongly correlated to the target variable. Even though it is there, it will not care. OLS algorithm will automatically convert the categorical variables to one hot variables and build a model. Okay, but we'll have control over it. Right? When we use scikit-learn and pandas, right, we'll actually do it manually. I'll show that. Okay, so don't be worried. So this is automated approach. It will actually do it, and then took all the features and built the model. Okay, now if you want to select features based on p-value, what you should do is look at the maximum p-value. Intercept, right? Remove intercept, right? And then build a model. And then again you will get all these features will have p-values. And look at the maximum, right? May not be this one. After removing intercept, right, the p-values will change because of the interaction effect. Okay, this term you need to remember, interaction effect. So when you are doing linear regression.
One second, sir. So we can actually remove a feature, but how can we remove the intercept? intercept is calculated, right?
Here we can specify that intercept is equal to false. If you look at the OLS algorithms API or any algorithms API, right, in linear regression and scikit-learn also, you will have intercept true and false. By default, it is true. If you say false, right, it will get get rid of it. Okay. If there is no option here, right, if in this particular algorithm the option is not there, you can ignore this and remove the maximum p-valued feature. Okay, then build a model. This intercept p-value will change. We have seen that before, right? When we built a model with only experience, we found that intercept and experience both are important. When we added the second feature, right, it actually changed, right? The intercept p-value changed. So like that, when you actually play with the features, automatically intercept will become important at one point in time. Did you get it?
Yes, got it.
Generally, intercept should be there. No, if intercept is not there, what will happen? So let me explain one more point, right? Let me take a screenshot and explain. I wanted to see both. No, I cannot show everything here, but no, I just put it like this. So I am talking about interaction effect and the p-value, right? Let me take a screenshot like 10. These concepts are really very important for data science. These concepts are, so when I say data science and artificial intelligence, right, if you don't have statistical data analysis and these pre-processing tasks, much pre-processing tasks, you can call the project as AI project. If these things are there, you call it as data science project. It is all mixed. There is no distinction between AI and data science. People are giving many names to confuse others so that they can make business out of it. By the time you understand it, right, they'll make business out of it and they'll do big things. So that's another way of doing things. So there is nothing big. All are same. They can call it as artificial intelligence, everything, including data science also. Especially these HRs are very confused. When I say we do AI services, right, they'll say we need data science, no AI, big data science. So they're getting confused, right? No relationship between big data and data science. Basically, big data is database, right? It is a big database. That's it. Whether you use MySQL, Oracle, it is kind of old style. And now we have the Mongo, Cassandra, these all things, big data environments. The what you call it as, I forgot the names. So that's fine. So people are getting confused. AI, we are actually doing AI, okay? And visualization, right? That Tableau, ClickView, and Power BI, they're all come under visualization. People are mixing visualization into data science and trying to sell. Right? They're making a 6 months course, time waste. Visualization can be learned in 2 days. Okay, you can do visualizations. You know what is histogram, you know what is bar chart, you know what is pie chart, and all that you can do. Right? So here, when you actually build a model, when you say fit, what it does, it is forming the equations with all the data we give and then solving it. Ultimately, what is it getting? The predicted salary, pred sal, is equal to some coefficient, right? Some coefficient. What is the coefficient here? Minus 84000 plus into 10 to the power of 4 means 13420 into what is this? Designation T director. Okay, plus minus 5120 into designation T dot junior dot, like that. It is actually forming an equation, right? So when I remove one particular feature and build a model, this p-value will change. right? Suppose that intercept I am not changing. When you actually remove intercept, right, what happens? What is it doing? What is the algorithm doing? It is actually, when your data is like this, it is trying to fit a straight line through the data. Okay. If your intercept is not there, right, this cut will not be there. So what will happen is the algorithm, the model will be like that, which goes through origin. When it goes through origin only, it may oscillate like that. See my hand. My video is not getting stuck, right? Right. The algorithm, the model will move like that only. It got stuck with the origin. If you don't have intercept, if you have intercept, right, it will have free hand. It will move anywhere, and the model will be more accurate. Did you get the idea? If you don't have intercept, what's the problem I'm trying to explain? Did you get the idea? In a linear regression algorithm, I always prefer having a intercept. Do you agree with it or disagree with it?
Agree, but oscillation point, but not clear.
If you don't have intercept, the line goes through origin.
Yeah.
Okay. So you fixed one end and trying to fit data, trying to fit the algorithm to their data. What happens? The line, right? It may actually go like that, or like that, or like that, right? Your data is somewhere here. At this point, I think whatever question you asked is right. Actually, you need to understand this. This data is like this, right? So when you are fitting this line, right? When you try to predict value for this particular x, what happens? It is going to be predicted somewhere here. Error is going to be too high. Right? For a data point which is somewhere here, right? If you try to predict, the prediction is going to be somewhere here. Error is going to be high. Do you agree? When you fix one end, whatever you do, right? The line actually oscillates only like that. When it is oscillating like that, there is more chance that you get more error, bigger error. Got it?
Yes, that's correct.
Got it, right? So when you have free hand, right, you took out the hinge this side and allowing the line to move anywhere, right? Allowing the line to move anywhere. Then what will happen? It will actually try to fit through data where the error is very low. It will fit the line through data where the error is very low, very low, very low. It is not going to be zero. You need to remember. Any algorithm will not give zero error. If algorithm is giving zero error, that means it is human. It is very easy for a human being to predict. Okay, just think about the statement I made. If an algorithm is giving zero error, if a model is giving zero error, it is very easy for a human being to predict. No need to build a model. Okay, just think about it. Maybe in future, maybe we'll talk about it. Okay. So intercept should be there. You should not be removing intercept. Even though the p-value is high, you should not be removing it. Okay, that's the point. That's the first point I'm trying to explain. So now what you need to do, if you want to make the model the best with this less number of features, you may have to eliminate some features. How do you eliminate? Look at the biggest p-value. I think down below it is there, right? And remove that feature. When you remove that feature, the p-value of the other features will reduce or increase. Okay, when you remove one feature and build a model, right, now we have like around 15 features. If you remove one and try to build model with 14 features, the p-values will oscillate. Why they will oscillate is there is a concept called as interaction effect. So we are building an equation like this. Suppose that the data set is like this. I'll actually use this x1 x2 analogy, right? X1 x2 and y. Okay, there are two input features and one output feature, right? There is a data set like this. There are many rows, m number of rows, right? And n number of columns. These are n I'll call, n number of features. Input features n, output is anywhere one. Okay, anywhere one. In some cases, we'll have multiple outputs also. We'll talk about them. Okay, so here m number of rows, right? So when you build a model, you can build a model like this, right? So you are trying to predict y cap. Y cap is the prediction, right? Y is the actual, y cap is the prediction. So when you are trying to predict there can be an equation like this, right? 10 plus 20x1 plus 30x2. Okay, this is one equation. Okay, there can be another equation like this. There can be, right, 5 plus 10x1 plus 30x2 plus 40x1 x2, right? 40x1 x2, a multiplication of two features, right? You can create a new column x1 x2, which is nothing but multiplication of these two values, put it here, build a model. It will build an equation with the three terms. Do you agree? When you are building a linear regression algorithm, what is happening? It is taking the features and trying to form the equations and solve them and find these coefficients, right? Find these coefficients, right? This is called as model, right? After finding the coefficients, you call it as a model. Before it's an algorithm, okay? So if you add a new feature x1, x2, the multiplication of these two values, you will get an equation like this. Right? I think I made it too clumsy here. I have this habit of writing and rubbing and all, scratching it and all that, striking it off very abruptly. That habit is there from my childhood. That's a bad thing. So 10 x1 x2, right? So do you agree with my statement? If you add a new column which multiplies two values and build a linear regression algorithm, it is going to add a new term like this. Do you agree with my statement?
Yes, sir.
Right? So we added a new feature. This is called as the interaction, the interaction term, right? Interaction effect and interaction term. If you want to explicitly add the interaction effect to the model, you generally create a multiplied feature. This is called as feature engineering. One of the ways of feature engineering. Feature selection and feature engineering. Right? Based on p-value, we are trying to eliminate features. Indirectly, we are selecting features. Right? Based on the interaction effect, we are trying to create a new feature. That's called as feature engineering. There are many other ways of feature engineering. Right? You extract number. You extract year from date. That is one of the feature engineerings. Okay. So there are other ways also. We'll talk about them. But this is one way. So this interaction effect, sometimes we have to consider. Okay, then there is an example in Introduction to Statistical Learning. There is a book called as Introduction to Statistical Learning. So that actually gives you a perspective of statistics and machine learning both. If you want, right, you can download it. It's a PDF. An introduction to stat with R it will be, but if you say PDF, right, you can actually download it. The Springer Publications it is. So in this, right, they actually took one example. It's a 400-page document. If you have time, right, slowly you can write, but don't waste time. Anyway, I'm going to cover everything which is present in there and which is very important to us. Okay, so in that book, what they did is, if you post an ad on a newspaper and if you post an ad on a radio, okay, the effect of radio ad and the effect of the newspaper ad, you collect it, right? The number of people the radio ad grabbed into the whatever to buy, make them buy, and the newspaper made them buy, and then looked at the total sales or whatever and tried to build a model. This may not capture everything, right? Because some people may look at both ads, right? TV, radio ad and the newspaper ad. Oh, this guy is very famous, it seems. People generally, if they see more ads, right, they'll actually buy it. That's what is happening with many places. When cinema actors and film actors actually become politicians, right? People vote because they have seen him before. They don't know really what he's going to do, right? Some people will have real passion and they'll do, right? They have done it also. Politics is not about the IAS officers, IAMs, and IITs. Anybody can serve people, but what I'm saying is generally human beings tendency is that if you see if you see something in many places, you tend to feel that I know it, right? Like that, some people may actually buy it. To extract that essence also and make the model work even better, you may have to add an interaction term there and build a model and try to make predictions. That way you will see how much sales is going to happen in coming days. This is one example which they mentioned in this particular book. Okay, so I think somebody asked about statistics and whatever, right? This gives you a perspective or a connectivity between machine learning and stats. I actually collected most of the stuff from there. Whatever we are seeing today and tomorrow, but maybe Monday, is all from this book only. Right? Beyond that, it is not that useful. Okay? So, did you get the point? Did you get the point? Interaction effect point?
Yeah, how to identify, sir, when there is interaction or not? There's any mechanism to identify?
Yes, we have. In the down below, right? We look at serial correlation. Sometimes serial correlation happens when you did not consider the interaction effect. Then try to add interaction effect there into the model, right? Interaction terms into the data set and build a model. It may actually get eliminated. The linear correlation, serial correlation will get eliminated.
Sure. And there is a possibility that X by Y also can be possible, right? We don't know.
Yeah, we can. X by Y. X by Y you should not be doing because you said Y, right? Y is the target variable, right?
Sorry, not sorry. X1, X2, you
can do X1 by
X1 by X2. Yeah.
You can, it depends on business, right? X1 by X2 when you do, it may be like, one feature is about the time and other feature about the number of resources maybe. Right? Then you can take the ratio, right? And put it as a new feature.
Sure.
Right? So it's a business. Basically the access wise, we are talking mathematics, but it is business actually. We need to connect that. Always we should be connected with business. Okay.
Sure, sir.
You all know, right? I'm actually trying to explain these things because some people may not know. Because people who are working in the industry, they already know. We should always be connected to business. Okay?
It's only two features combining, or it could be more than that.
More also. I will come to that. When you do polynomial regression, we have tools. We have actually classes from scikit-learn which actually does automatically.
Okay.
And then one more point here is, I'll talk about this more when I talk about gradient descent. Right? If you look at this coefficient, right, this intercept, it is a negative number. And if you look at the coefficient of this number is negative, right? When a feature's coefficient is negative, it is negatively affecting the model, or negative correlation is there between that particular feature and the one we are trying to predict. Okay, got it? When the coefficient is too big, either negative side or positive side, the strength is more. When the coefficient is too small, the strength is weak. So this equation will explain the strength of the feature also. Okay, all the features all together combined. Okay, we'll come to that also in future. Okay, just leave that for now, because if we go into that area, right, we may not be able to come back, and there are other areas we need to cover before we understand the coefficients effect on the feature. That is the way we are going to go about. The p-value based approach is not right, because when we looked into the p-value, how the p-value is getting calculated, it always tries to consider one feature and the target variable and try to do the hypothesis testing and tries to find the p-value. It is between 1 and 1, right? But as a whole, you need to see. So these p-values may not be right when the assumptions are not satisfied by the dataset. Okay, I said that there are 5 assumptions of the linear regression algorithm, and when you want to look at the p-values and select the features, the assumptions of the data, assumptions of linear regression should be satisfied by that data. Then only you can take these p-values seriously. Rather, you cannot take these seriously. That's where p-value based feature selection we will not use. I will not use, and industry is also not using it. Some people who are very familiar with R and they do R language thing, they do it, but that is not right, because data always may not satisfy linear regression assumptions. Got it or confused? Got it?
Yeah,
I'm
sure, sir.
moving. Yeah, I'm moving
Just
on.
1 second, sir.
Yeah.
The standard error, all those things we can completely ignore, or anything we need to really pay attention to. Standard
No
error.
need. No, I actually tried to explain that because you know the standard error, you know the standard deviation, you know what is t statistic, what is confidence interval. You need to get more hold on this terminology.
Sure.
So to make you more aware and remember them well, I actually tried to explain it.
No, that's not my question, sir. So in terms of fine tuning the model, whether to take out some columns or those kind of things, I know we are paying attention to the p-value. We don't need to worry about standard error at all.
No,
Okay,
because p-value is the ultimate result, right? After all those, using all those numbers, we actually came to a conclusion of p-value.
Agree.
We are using p-value, and in real time, we will not use this algorithm or this approach. But in interviews, they may ask, and we wanted to solidify the statistical concept. So we are.
Sure.
I think you are right, and I am right. But
sure, sir.
Your concern also I got it, but now when there are too many concepts to learn, you need to understand where to focus and where not to. That's my worry. And if you focus on an area which is not that important, right, you may lose grip on the area which you need to focus on. Okay.
Sure.
So linear regression. So first assumption is linearity. Okay. So it assumes that the input and output both are linearly related. Okay, so this is one important concept you need to understand and remember, right? So how to know whether the all input variables and the target variable are linearly related? The solution is that you need to build a model first. See here, I used scikit-learn linear regression. You can use this one also, right? Whatever model we have here, you can use it. But for fun, I actually use this. Okay, so I am using scikit-learn's linear model, sklearn linear model. From this model, so from this module, I'm importing linear regression class. I created an object. Till here it is an algorithm. Then I fitted it with x and y. What is x? I have taken all the input variables, and I took some sample data set to show you on a nonlinear data. When you build a linear regression algorithm, what happens? Okay, why am I showing you this? Is I am saying that the linear regression assumes data is linear. Data is linearly related to input and output. Okay, but how to find whether the data is linearly related to output or not? I am taking a nonlinear data set and building a linear regression model and fitting it and trying to see how it behaves. Based on this, right, we'll actually understand how to take it from a huge data set. Okay, so I've taken a simple synthetic data set where I have got only one column x and one column y. Why I took this way? Because when there is one input variable and one output variable, you can see how those two are related, right? By doing like this, right? X1 to y, you can do a plot and you can understand how they are related. You look at the blue dots. These blue dots are the data. Okay, don't look at the red line now. Okay, these blue dots are the data. Are they linearly related or non-linearly related? Linear or non-linear?
Non-linear.
Non-linear, right? Linear relation means data will be, forming a line like that. Okay. Non-linear means some pattern, right? Some pattern. The data may be like that. or maybe like that. Non-linearity means any pattern. Okay, so here if you look at this data, we fitted a straight line through the data. This is the best fit line. When I say best fit line, you can draw a line like that or a line like that, or many lines you can draw. But out of all those, right, this line is giving you the less error. This red line is giving you the less error. That's the best fit line. Okay, we call that as best fit line. Okay, so if you have to build a model, right, you have to build a perfect model, right? You should be building a model like that, which actually goes through all the data like that. Right, if you are able to do a model like that, right, it will give you the least error. Do you agree? This curved line. Do you agree? Do you agree?
Yes, yes. Yeah.
Can we do this? Can we do this kind of a line?
Maybe, but not with linear regression, I believe.
Not with linear regression. Polynomial regression we call it as. The concept is simple. Y cap is equal to theta 0 plus theta 1 x. If you say, right, x1, it is a linear regression. If you say y cap is equal to theta 0 plus theta 1 x1 square, you call it as polynomial regression. Second degree polynomial we call it as. If you can form this kind of an equation, right, you get this kind of a line. How to form that kind of an equation? Just now I explained, the previous thing. You have x1 and y, the data, right? If I want to form x1 square, an equation with x1 square, what should I be doing?
Data engineering, adding more features with the existing features.
Yeah,
Add
adding
one more column, you add one more column as x square.
Yes, good, very good, right? If you add one more column x square, right, it will be doing like theta 2 x1 square and theta 1 x1. But if you remove x1 and just put x1 square and y, you will get that even this one is also a polynomial. It will also form a parabola only. Second degree polynomial actually forms a parabola. That is polynomial regression. Okay, so before we go there, right, if you look at, I have taken only one x and one y. I tried to plot it. I tried to do a scatter chart. It actually formed a parabola, and I tried to build a model here. Right? I tried to build a model here. I made predictions. Right? I took the predictions and tried to do a line there. See this here? PLT dot plot of x comma y and b dot. That means blue dot. Okay. B is the color and dot is the. I wanted to put a dot there. Okay. And then PLT dot plot x comma predicted r. Right. If I don't say b dot or anything, right, it's going to do a line. Plot method will do a line. So x and predicted. See these predicted values. I built a model here, right? I trained a model here, and then I passed x and made predictions, right? I used those predictions for each x. For each x, what is the prediction? For x, what is the prediction? For x, what is the prediction? Like that, I actually dotted and then connected all those dots. So that is the line. So this is the best fit line. This is the data. On a simple data set, you can actually do this plot. When I say simple data set, only one input variable and one output variable, you can do this plot. If I have 10 input variables and one output variable, can I do this plot? 10 input variables, x1 to x10 and y. Can I do this plot? Can I?
It's taking only one input variable.
Yeah. This is a two-dimensional plot, right? This is a two-dimensional plot. Yeah, if you have one more input variable, right, you have to do three-dimensional plot. Got it? Got it or not? If you have one more, so x1, x2, and y, if you have to do a three-dimensional plot. x1 on x-axis, x2 on y-axis, y and z-axis. Got it?
Sure, sir.
So if you have 4 input variables, right, you have to do 5-dimensional plot. If you have 10 input variables, right, you have to do 11-dimensional plot, right? So it is not possible. So you will not be able to understand whether data is linearly related or not. Okay. So linear regression is assuming that that data is linearly related. How to find whether data is linearly related or not? One way is that you build a model, right? You build a model, make predictions, and look at the residual. If the error is too huge, what that means? Data is not linearly related, right? Do you agree?
Yes, yes, yes.
Okay. So when you build a model and make predictions and look at the error and calculate the total error, and the total error is too huge, that means data is somehow very scattered, and then you are trying to fit a straight line through it, and the predictions made on the line, are very far from the actual values. This value is somewhere, for this x, y is somewhere else, above somewhere. For the same x, the prediction is somewhere here. So there is a lot of gap. So it's going to give huge error. That is one way that all input variables are not strongly related to y. I made a statement here. All input variables, I made a statement. Is that true? Are we getting that perspective by looking at the error residual? All input variables together, they are not linearly related. When the residual is high, total residual is high. Is that a right statement? What do you think? Yeah, right. Any questions about the statement I made? Okay.
Can
So
you please brief it?
yeah. So you took a data set, 10 input variables and 1 output variable. You built a linear regression algorithm using 10 input variables and 1 output variable, and you made the model predict, and you calculated all the residuals and summed it up, right? Squared or summed or absolute value or sum. Okay, you got a huge error. What that means? That means linear regression algorithm, the line you drew through the data is not matching with the dots, right? Matching with the original data, right? Original y. Do you agree?
Yes, that's correct.
If you are getting 0 error, or maybe an error close to 0, or R square score which is close to 1, what that means? All x's are linearly related to y. Right? All x's together linearly related to y. Right? Yes or no?
Yes, yes.
When error is small, the data is satisfying the linear regression assumption. When error is huge, the data is not satisfying the linear regression assumption. You can actually take the error as basis and understand whether data is linearly related or not. If you understand this point, right, I'll go into the next stage and try to show you one plot, one graph which actually explains clearly. The error, the residual actually shows you, or residual will have signal to identify whether the all input data, all input features together are related to y linearly or not. This statement, did you get it?
Yeah, when the add when the when we add the term all, then it's kind of
Confusing.
yeah. So because we plot with only 2-dimensional, right? There it's very straightforward.
I'll come to that.
Understand
Don't be worried about plotting. I'll come to that. I'm actually preparing your thought process so that when I show that graph, right, you will get it. The basis is when you look at error, are you getting the signal or not? If you understand that point, right, I can go forward.
Yes, please go ahead.
Right? So when you look at residual or the total error, you are getting that signal that whether data is linearly related or to y or not, you are getting that signal. So you can take residual as the basis. Okay, so let me show you that. This is called as predicted versus residuals plot. Initially what I showed, 1x and 1y. When you have only one input variable, one output variable, you can do a two-dimensional plot and understand the relationship and see whether linear regression algorithm fits or not. But when you have more than one input variables, you should rely on error to understand whether it is linearly, to get the signal whether the linear relationship is present or not. So we are taking the residual as the basis and plotting one graph to understand the pattern. See this here? I took predicted values on y-axis, sorry, x-axis, and error on y-axis. Okay, this is standardized error. I'll talk about standardization in a moment. Okay, so is that a standardized error? Give me 1 second. Predicted value. Yeah, it is not standardized error. It's just error only. Okay, so I should take out. That's okay. So I'll talk about standardization later. But I am doing this plot. If you look at this, I made some prediction. Okay, this red line, right? It is at 0. Okay, ideally, right? If linear regression algorithm is working, I'll make two statements. Ideally, if linear regression algorithm is working or all input data is linearly related to y, when you make a prediction, where the error should be. So on y-axis I took error, on x-axis I took prediction. Okay, when you make a prediction, ideally, where should the error be?
0.
0. Everybody agrees? You guys should agree or disagree. Why only 5 people joined today? I don't know. You should agree or disagree. Do you agree with the statement what Giri said?
Yes.
Right. So when the error, for each prediction, when the error is not falling on 0 or close to 0, what that means? The data is not linearly related. For this particular prediction, the error is somewhere here. For this particular prediction, the error is somewhere here, like that. So I'll make another statement. When you look at this plot, right, it is actually resembling the relationship between input and output. See this? This input and output has got the curvy pattern. Okay, and predictions and residuals also have the same pattern, right? When you have one input and one output, you can actually do this plot. But when you have multiple inputs and multiple outputs, you cannot do this plot. So we actually rely on this plot to see the relationship between all input variables and output variables, whether it is like this or any other pattern. This is called as residuals versus predicted plot, or predicted versus residuals plot, which actually gives you a clue on how the input and output are related together. All inputs and one output are together related. It will give that whatever. Got it? If you see this here, the prediction is here, the actual value is there. When you take the error, right, it is going to be far, right, far up there. Okay, the actual value is here, prediction is on this line. Again, the error is high, so it is somewhere here. The prediction is here, actual value, sorry, prediction is here, actual value is here. When you take the error, it is going to be somewhere there. So whatever pattern you see in the relationship between the input and output will actually be represented by predicted value and the residual plot. Predicted value and the residual plot, because because this is the point here, right? The predicted value and the residual are actually resembling, right? When the data point is too far from the line, the dot is going to be too far. When the data point is too close to the line, the error is going to be close to 0, right? So ideally, these dots should actually fall around the white line if the data is satisfying linear regression. If it is not right, it is going to be like this. And this is the pattern in which the input and output are related. Whether you have one input or 100 inputs, it doesn't matter. You will get only one residual and one predicted value for each data point. It's a consolidation, right? You have got 10 inputs, one output, you built a model, you made predictions, you calculated error. So the total data, right, the 11 records, so 11 columns, we actually consolidated to 2 columns, predictions and the error. When you do a plot between predictions and error, right, that actually resembles your original data's pattern. So visually, if you want to see all input variables and output variable, how they are related, you should be doing predicted versus residual plot. Did you get it?
Yes, sir.
Right. So this is a simple example I have taken to explain you practically how it looks like. Okay. So I cannot on a multiple input variable. So if you look at one input, one output, and I took a parabolic shaped data, and then I try to build a model and try to look at it is actually resembling. It is not the same, right? If you see the tail, right, one side it is high and one side it is low. You will get a high level view of how the input and output are related. Okay, if you any place, if somebody asks you, I wanted to see all the inputs how they are related to output, you should be building a linear regression algorithm, linear regression only, and then build, the build model with linear regression and try to do residuals as a fitted plot, and you show this plot and this is related. Only regression algorithm can do this because you do a straight line, right, and then you actually calculate error. If you do a curvy line, right, you don't know, whether the pattern is like this or not. Only linear regression can explain this. Okay, that is where I said linear regression algorithm is used for inferential purposes rather than building models and putting in production. Got it? This is the inference we get.
Sir, this particular graph of residual versus predicted, we can actually build this for anything. It need not be linear regression problem, right? For anything, we can actually calculate the predicted versus residual.
We should be. That's a good point. First, whenever you get a regression data set, first thing you should be doing is fit a linear regression algorithm, do a residuals versus fitted graph, and look at the pattern. Then you will understand which algorithm to go with.
Perfect. Clear.
Right? You got the point actually. If the data is like this, right, you need to build an x square equation. If the data is like S shape, right, you need to build x cube equation. If data is not having pattern or it is having very complex pattern, then you should be going with a random forest kind of complex algorithm or boosting algorithms, which will actually make the weak learners strong learners, or a deep learning model if you have huge data. So these are all different concepts of selecting an algorithm. I actually pointed out 3 things. We'll cover more, right? So the data scientist problem is that you need to do pre-processing and convert data appropriately, then try to understand data as a whole and select an algorithm. You may get multiple algorithms choices. Out of 100 algorithms, you may think that 4 or 5 algorithms are working. You need to experiment with all those 4 or 5 and choose the best. Okay.
Okay, sir.
So you got it, right? Anybody has got any questions or what Giri is saying? Did you guys get it? Linear regression algorithm is the algorithm you use first on any regression problem, and then look at this residuals versus fitted graph. It may give you, maybe 80%, 70% of the times, it may give you a clue on how the data is related. Depending on the data relationship, you can actually choose the algorithm. Okay. So that is residuals versus fitted plot, and I have taken our data, right? Our data, salary data, and the input data, and made predictions and calculated, the residuals as the residuals, and then I am actually plotting, right? I am actually plotting a graph between observed versus predicted values. You can actually do, the actual values and the predicted values also you can do. It will also show you the kind of pattern only. Okay. observed value somewhere, observed value is 2 or your original value is 2, your prediction is 100, it will actually oscillate like that. The dot actually goes above. If both are 2, right, you will get a line, 45-degree line, 45 degrees, right? If both are same, you will get a 45 degrees. If one is not, one is not aligned with other, one prediction is not, the predicted value is not close to actual value, the line will go like that. So let me take a, simple graph and explain. If your, some x1, x2 and so on, xn are there, and y
the
is
observed value and the actual value both are same.
Yeah, that's what I'm actually trying to do. Both should be same. Observed value and the predicted value. Yeah, I think observed value and the actual value are same. It's a different terminology.
Terminology. Okay.
So if your y and y cap are like this 1 1 2 2 3 3 4 4, what will happen to the plot? You will get like that, right? The dots like that.
A straight line from 0.
Right? Yeah, it's going to be 45-degree angle. If your predictions are like, y cap is like this 1 10 2 maybe 3, maybe 3 maybe 15 4 maybe 16 like that. That actually is 1, predicted is 10, so it is going to be somewhere there. Actually is 2, predicted is 3, somewhere here. Actually is 15, the actually is 3, no, predicted is 15. Actually is 4, predicted is 16. So your data is like, your graph is actually too much oscillated. If your model is working well, it should form a 45 degree, it should be around the 45-degree line. If your model is working well, it should be around 45-degree line. If you do observed versus predicted value plot. If you do observed versus predicted value plot, your data, your ultimate graph, the scattered plot, the dot should come like this. That means the model is working good. If the dots are coming like this, right, this blue thing, the model is not working good. Okay, when you do observed versus predicted value. When you do residuals versus predicted plot, right, all the data, all the dots should be around this 0 line like that. Because it is error, right? The y-axis is error. Error should be close to 0. Okay, got it? Difference between this observed versus predicted value and the predicted versus residual plot. Any questions?
But yes, go ahead.
No, please go ahead.
Oh, thank you. So, but will we get this y and y cap 1 and 1? So it won't be the case, right? So it may be in 45 degrees, but it may not be exactly. It may go like
No, I just
50 degrees or 30 degrees.
Yeah, I'll go extremes, right? It will not be 50 degrees. Your line, your red line is always going to be 45 degrees. Your data, whether it is coming close to it or far to it, that actually shows you whether model is working good or not, or the data is linearly related or not. Your dots may come here or close to it. If it is coming like this or like this, the model is not working good. If it is coming like this, right, the model is working good.
Okay.
Ideal case is that your prediction should be equal to your actual value. Ideal case. That will not happen. That will not happen. Okay. That's where I'm saying should be around the line. Got it, right?
Yes.
So you can use either this plot or that plot, but generally, in industry, that residuals versus predicted plot is the one. When you look at this plot, right, what I did is, when the residual is greater than 5,000, when the error is greater than 5,000, I'm actually, trying to look at the index here. The index of that record, I'm actually plotted on the chart. So 9th record, 30th record, 20th record, and 28th record, the error is huge. When I say error is huge, right, those data points are very far from the the fitted line. Okay, they may be outliers. So you can use the linear regression algorithm to find out whether there are outliers or not. Outliers means the y value or the x value is not properly inputted, or the devices got corrupted and they got into the data, or the pattern is not matching and you may have to go with other algorithm only for those data points or as a whole data set. Got it? To the whole data set. Got it? Outlier analysis we call it as. We can use algorithms to do outlier analysis also. Okay. This is one example I actually did.
So we can take out outliers also if we think if we really feel that they are some exception case and all, right?
We need to look into them. Outliers, we need to look into them and see what the problem is. If the problem is real, we need to fix it. If the problem is not real, we should be keeping it and try to maybe transform data and try to build the model or change the algorithm.
Okay.
Right. So when I say we need to look into it and see whether the data is correct or not. If you take the real estate data of Hyderabad, all the Hyderabad real estate data will be in one range, and Banjara Hills, Jubilee Hills will be another range. If you try to fit a model for both data, Banjara Hills, Jubilee Hills, and the rest of the Hyderabad, and try to build a model, that data may not fit into this. So you may have to separate the data and build a model, or you have to choose another algorithm, which actually generally in this particular scenario, whatever the example I said, you need to separate Banjara Hills, Jubilee Hills data altogether and build a separate model for that. Build a separate model for this. When data comes in, right, you need to look at the data, right? Redirect the data to appropriate model and make the prediction, show you the result. Got it?
Yeah, sure, sir.
Right. So that is
one more question, sir. So once that residual, predicted versus residual is looked at, and if there is too much of deviation, then we need to revisit the model or take a
data.
relook at it.
First, we need to look into the data. This, right? Only 4 points are violating, or maybe 100 points violating. Out of 1 million, maybe 1,000 points are actually violating. We are actually trying to reduce the area of analysis, or the magnitude of data, the amount of data we need to analyze by using these tools.
Sure.
Okay. Initially, the normal distribution, and box whisker plot and all that stuff to individually analyze columns and see, the area to reduce, and then look at the records. Now we are all together combined. We are trying to see. That's where I said initially when you are doing the analysis, you will not take solid decisions. You will do dirty models and then look at this as a whole. You see, try to fix the model. If it is still not working, you go back and try to look at the individual columns. It is all back and forth, back and forth. There is a methodology called as CRISP-DM. In data science, we follow. I think in our presentation we already have it. So this is actually mining and other. I think the abbreviation. Cross-industry standard process for data mining. Okay, so this is the process we use in data science projects or machine learning AI projects. You take data, understand it, prepare it, model it, evaluate it, come back, and again understand business. Come back. You actually do back and forth here, and once you are satisfied, then you deploy it. Okay, so this back and forth stuff I am actually talking about. Modeling data preparation, and understanding data, like that. So when the model is not working, either here or here may be the problem. That's what even in our diagram we actually showed. Yesterday I showed you that diagram, right, in our demo. That diagram is based out of this only. The whole industry follows this. Okay, so CRISP-DM we call it as this one. So I am actually doing back and forth, right? So here back and forth I am doing, again here I am going back, so I am actually doing back and forth here also, collecting data and analyzing, collecting data. The diagram is represented in a different way, but essence is same. Okay, so here, right, we used the linear regression algorithm, and then we did residuals versus fitted plot, or predicted versus predicted versus residual or fitted, we call it as predicted, also called as fitted versus a residual plot. If you look at this, right, these two data points may be outliers, you can analyze. And when you look at the y-axis, right, it is actually standardized value of x. What is standardization? I'll explain it a little bit. Z-score of each data point is called as standardization. If you look at this formula, what I did, I passed residuals here, standard scaling, I passed a residual, I calculated mean of it, I calculated standard deviation of it, I'm calculating z value and returning it. For each record, for each data point, for each residual and for each prediction, I'm calculating z-score. That is called a standardized value. When you are doing this predicted versus residuals plot, right, it is always suggested to use standardized values because the range will reduce. When you calculate z-scores, right, the range will come back to maybe -20 to 20, even though original data is too huge. And when the scale is shrunk, right, in both directions, your plot will be more evident. Okay, I took one example, I think previously. If you have, yeah, I'll explain that again. This is very important. This is very important part. When you are plotting something, right, and on the x-axis your scale is on x-axis and y-axis is 1000. Okay, and one value is ranging between 5 and 10, right? X value is ranging between 5 and 10, and y value is ranging between maybe 500 to 1000. Then what will happen is all these data, all these 5 and 10 points will actually get stuck with the x-axis. Do you agree? Right, the x values are all around here, and y values are around here, right? So all get stuck with here, right? All these things will get stuck with the y-axis. Do you agree? When you do a plot?
Yes.
Right, but when you standardize the x and y, one way I said is take the maximum and divide all the values, take maximum and divide all values. What will happen? The scale comes between 0 and 1. Sorry, 0 and 1. Right? Then the graph, the dots will become more evident. Right? They'll come out of it. They'll come out of the y-axis and clearly visible there. So that's what we are doing here. When I did standardization of the predicted values, residuals and the predicted values, I am trying to make the graph as clear as possible. Okay? By fixing bringing all the data to similar scale, I'm actually trying to make the graph more clear. When you take standardized data and build a graph, that actually shows you real pattern. If you don't standardize it, that may actually distort your results like this. This is an extreme example, but in general it will not happen. It may look similar, it may look okay, but there may be internally problems. The solution is that always try to standardize it and try to look at it. Okay, so I'll actually make one point.
Yeah, calculating the z scores to z scores here is one of the normalizing way, right?
A normalizing approach. Dividing with maximum is one way. Taking z-score is another way. We'll see min-max scaling and other scaling approaches. There are basically three only. Basically three we'll use. Min-max and standardization, and the z-score is called standardization or normalization. And then dividing with maximum, that's another way. Okay. So here
done for x-axis also, sir?
Yeah, both.
Okay.
Both you have
x and y. Okay, sure.
Yeah, I did for both. When you don't do for one, right, the dots will get stuck. Maybe like that or like like this.
Sure.
This point is very important. This is used in many algorithms. SVM, k-means clustering, deep learning, right? Definitely will use it. And gradient descent algorithm. This concept, whatever I explained right now, the standardization concept is very important. They're small things, very small things, but they make a huge difference when you actually look at the total A. Okay, so ultimately, right, when data is not getting fitted properly, you may have to do transformation on X. Either you have to add X square or in this case, it will work. Right. So you need to apply transformation to X to fix problems with linear regression, linearity assumption. Okay. So the problem how to diagnose I explained here, right? How to diagnose and then how to fix it. Okay. So for all linear regression assumptions, we'll actually go like this. Okay. So when you have understood this residuals as a fitted plot, so we can actually easily understand the homoscedasticity or heteroscedasticity problem thing. Okay. I'll explain this Monday. I think today is Friday, right? So any questions, right? You can ask. I'm going to stop it.
Sir, so far